Good afternoon, everyone. I'm doing this presentation from deepest Dorset, so I'm hoping we'll still be able to keep our communication going. I'm part of a team which is part of a partnership between the University of Southampton and Thales UK. The photo image on the right of the screen in this stage is where we are reporting the results of this project to the partnership board. So I'm going to hopefully take you through some of the motivation behind the project and some of our results, and particularly deal with the challenges that we faced when trying to get maritime autonomous systems to collaborate. So we see the world as being not just about the autonomy or autonomous systems based on a single vessel, but exactly how those vessels will interact in a particularly in a safe and secure manner, as we were sort of taught. The first presentation today was looking at, and also by the nature of the marine assets or vessels. As you can see, the picture from Cowes Harbour, multiple sailing vessels, some moored, some moving, a variety of vessels, some going slow, some going fast, different directions. It's a very heterogeneous system. There's many environmental constraints. The speed and maneuverability of each vessel is dictated by its design. And for the assets we're talking about here, which typically tend to be small, they have limited energy supply. So these all sort of motivate a desire to understand how they can collaborate effectively and, for want of a better word, to sort of achieve a mission, some kind of goal. So just an overview of the paper. We're going to give a little bit of some of our thoughts about maritime autonomous systems, and then concentrate primarily on our integrated mission management system project 2019, and how we designed that, how we prepared for trials, the trials themselves, and then draw together the conclusions at the end. So again, the last two speakers have articulated this very well. We expect future ships will use ever greater levels of autonomy, both for systems based on each vessel and also how they interact remotely with other vessels and back to shore control stations. Now, as with driverless cars, it's going to be very critical to safety how these kind of interactions occur. So we wanted to explore this as sort of a stage one exploration by taking some of our assets and seeing if we could get them to work together and collaborate effectively. And there's nothing better than getting out on the open water and trying things for real, as we definitely found out in this this project. And so we decided to be reasonably ambitious and try to combine an integrated air, surface, and subsea operation. So, MAS systems, I don't need to sort of sell them too hard. From my perspective, they offer the potential, two things: potentially reduce operational costs if it's done effectively, and crucially to take people out of harm's way. The maritime environment is one of the things that will distinguish this sector from many other autonomous sectors. Our spatial and temporal scales are very large. We've got crossing the Pacific, we've got missions that last months. This poses a whole series of challenges, particularly when you look at the other ones that we have to deal with, sort of the fact that energy supply limits our speed and range. Communication, even out at sea on the surface, is still quite limited and very costly, even with current and expected satellite systems. And it becomes even more so when you go underwater. Localization and navigation underwater is a real challenge. And yet the systems have also got to survive extreme conditions and operational limits. So what we want to be able to do is to have trustworthy decision-making and control. And we see this as being really one of the things that we wanted to investigate in quite a lot of depth in this project. So the motivation. So those of you know of Unmanned Warrior and similar exercises will realize that the assets typically deployed in those came from many organizations, would typically take many people looking after one vessel or asset. So that's the model at the moment. So autonomy of a fleet of vehicles takes a lot of people, therefore it's not very cost effective. So we have to move over to the right. We have to have the ability for a few people to control many, many vessels, so they can collectively work together. So the IMS 2019 project. So we wanted to create pretty much from scratch an integrated mission planning system. We wanted to test its operation, not just simulate it, but test it, using the low-cost multi-vehicle assets Southampton has. And effectively, the system needs to be able to be allow a single operator or single operator control station to control multiple assets, and it's designed to be scalable, reusable, and flexible as the mission requirements will change. So originally, we set out with the hope that we could have a surface vessel, we could have an eye in the sky, we could have a surface vessel which was controlled from or sort of interacting with the host ship, and then we could have multiple underwater vehicles. So the system design, and it always makes it very difficult for a presentation when you talk about system design and software design. I'm not really going to show any software. It's focused on the critical issues here as the interfaces between all the system components, communication channels, ways that messages are passed backwards and forwards, ways that assets are primed to start a mission and communicate once they're underway. So this was the message was sent by Thales, as set by Thales as a challenge, and we wanted to be able to plan missions, after we've identified the goal, execute it, and then be able to review how well the mission was performed. And I say trustworthy autonomous systems, it's one of the areas of expertise at Southampton. I'm very fortunate to have a very strong team in electronics computer science who helped us with this, looking at the use of formal methods and such to actually verify before you set out that it's going to do what it's supposed to do. So again, there's a little bit of a screenshot here of some of the bits of pieces of the system. So we've got a user interface for creating planning, previewing, live monitoring, and recording missions. We've got software to deal with planning and optimization, software to deal with validation and verification, and then a kind of an approval process to say, we've all checked it out, looks good, let's go ahead and implement the mission, execute the mission via the assets and the interfaces. So just to sort of be aware on the trials preparation, this took a large amount of time, and it kind of indicates the challenges we face when we go towards autonomy in the marine space. We had a 4-month lead time, which was pretty challenging. We based the trials out of Thales' UK Autonomy Centre at Turnchapel Wharf in Plymouth. We had access to a really nice hangar to securely store the assets, a workshop, and to be able to recharge at the end of each day. We had an RHIB Clyde of Dartmouth as our control vessel out on the water. Had to modify it a bit, so we had some mains power sockets so we could plug laptops and various other bits of kit into it. It's a kind of relatively small vessel, so the conditions were not great sometimes. So the trials area, for those of you who don't know Plymouth Sound, Turnchapel is over to the east. Across on the west, there's a designated testing area for autonomous marine systems. We had a triangular area which we'd set out. We were using the air asset from, had limited range because we didn't want to go with our really big aircraft because they're actually quite challenging to find a launch site near enough. So we went for a small site close to the testing area, but that did mean that we were quite physically separated from the people in charge of the air asset and from the people setting out from Turnchapel. So we're very grateful to East Cornwall Scouts for the loan of their campsite. As you can see, the weather during most of the trials was not perfect, misty, quite a bit of chop at times, and as we'll see in a bit, that's quite a slopey site. So the assets, just going through these quickly, many of you will have heard of these before. EcoSub Robotics is a really nice underwater vehicle, less than a meter long, designed to operate for a reasonable amount, up to 12-hour duration. It's designed effectively as a cheap, low-cost asset. You can deploy a number of these simultaneously, and they can do a survey and report back. Again, the L3 Harris CCAT-3, which EPSRC funded for Southampton, 3-meter long Cataran, again, a great vehicle for testing out autonomy in the real world. And then, again, Southampton's sort of expertise in UAVs and development, as we've been doing this for sort of 10, 15 years now. Salsa is so it's a principal aircraft. It's quite small, 4 kilograms, and that was a vehicle we designed to use with our experiments. Unfortunately, we had an incident. Okay, so then we had this replacement vehicle. Again, it's brought down at short notice, but we managed to integrate the system with that and get that working. So now, those of you who've done safety cases will know that these are not trivial, especially when you're operating in the real world with other people in the vicinity. So it was a really critical part of our project, and we learned a lot through that. We had to go through 2 organizations. We had to go through the university's pretty rigorous safety case process first, and we had some pretty long documents put together. Once it was approved by the university, it then went to Thales because it was running from their site. That was then approved, and we were good to go. That good to go decision came pretty much right on the first morning of the trials, so it was a little bit bad for the nerves on the weekend. We had to get permission from the CAA to operate our unmanned aircraft systems. We had to serve notices to mariners of the disruption in the trials location. So the weather forecast, these tech trials were in October. Anyone who knows what the weather's like in the southwest in October knows that we have quite variable weather. It was good enough, but it wasn't great. We didn't get lots of sunshine. We had quite a lot of wind, quite a lot of gust, and yeah, it kept us on our toes. The planning of the trials, we were very lucky to have the Hydrographic Office support, so we had detailed data for the test area, and in fact that proved very valuable at one stage when our mission was planned outside of the bathymetric data, and we found the seabed was too shallow from the Hydrographic Office, so it allowed us, our checks worked at that stage. Each day we had a playbook describing all activities proposed and considering the likely weather conditions. And, you know, actually those playbooks had to vary as we went through and found what worked and what didn't work. But it was a 5-day process. Everyone came away pretty exhausted at the end of those 5 days. We aim to build confidence by getting more and more complex trials carried out. We had lots of communication issues between the assets, even though we tested them before we went down. Lots of software updates. We're very grateful to companies providing software updates live, as it were. So we made some pretty rapid progress. But key achievements, we did have the ability, all the assets and the base stations, to all be in continuous communication. And that was a really important outcome from a mission system perspective. So the UAV operations, I'm not sure whether the video is going to actually play. Let me just play that from here. So this is showing the tricky landing of the vessel, of the aircraft coming into the scout campsite. It's breaking up a bit, but if you can see that shot there, it's quite steep. And unfortunately, on one of it, we had to, because the wind direction came in over the trees, and the first vehicle had a very heavy landing, so we had to bring in the bush mule to replace it. Again, just go to this. Now, it's different, as I said, software. So this is just us walking through using some of the software we developed for a mission plan. So clicking out the live positions of the different pieces of the routes that we wanted, or weight markers we wanted to follow. So again, it's quite, we previewed the mission, simulated it for the aircraft. This is showing you what it was going to do. That funny king can go round and orbit, avoided. So again, apologies if this is breaking up, but we've got from the synchronized cameras from the aircraft as it's flying around. You probably can't see the assets on the ground from this, but they were there. There's a little bit of a flash there to say that they were there. So again, this is really good from a sort of post-mission analysis perspective. So that was the aircraft's plan. We also then had the USV and what it was setting out to do. And again, we approved that mission. Sorry, yeah, the internet's breaking up again. And you can see some video of the USV in action. So I'm going to go to the next slide because I think these videos are a little bit problematic. So this is just to give me a bit of a pause whilst we I prepare for the. So this is a nice video that Talis put together. Again, hopefully shows you some action from the trials, talks through the weather, or shows you some of the conditions, the vehicles. Yeah, it's not really doing very well. So I'll just give it a pause and I'll go to the conclusions. So I'm nearly there, Dimitri. Hopefully I'm just about on time. And so yeah, we had a team of 16 on site. We towed out the vessel to the start of the trial location, which is a bit more sheltered water. And we kind of nearly there. So I think that's probably, so we consider the trials are a success. It was very challenging. The Turnchapel site was an excellent place to be based. We're due to go back, or we're due to go back pre-COVID. We're heavily at work still, but lab-based at the moment, or not lab-based, home working based with the software. So I'm just going to bring us to the conclusions. So we use low-cost multi-vehicles to really get this up and running. It was a great team building exercise between the two partners. Getting the trials completed taught us an awful lot. We could plan, execute, and multi-domain missions. It was possible. We had really, as many of you who've done field robotics will know, the challenges really come when you actually put the assets in the field. But therefore, that's always a critical part of any development. It was the proprietary systems, but we're going to live in a world of proprietary systems. So we have to work out ways that we can join proprietary systems together. Open interfaces, common, those kinds of, automotive's quite good at developing those. We need to think about that in maritime. Communications, as we're finding today, still provides challenges. We think that looking at collaborative behavior in this kind of way will really help us going forwards to large ships, as well as just the specific assets we looked at in this project. I'm going to acknowledge the big team. There's a group of academics at Southampton put a lot of time into this, but really the hard work was done by the people on the ground through those 5 long days. And here you can see they're all celebrating the end, perhaps just with relief as it was all over. I'll thank you for your attendance.